Let's build a k-means clustering model in Python so you can better understand how it works. Imagine you run a tiny cafe and you're trying to organize your loyalty customers into groups so you can send better recommendations. You don't currently have labels to designate these groups of people like remote workers or regulars. You only have their behavior data, like how often they buy coffee, what time of day they usually come in, and how much they're willing to spend. This is exactly the type of situation where the k-means clustering machine learning model comes in clutch because it can organize people based on similarity without needing pre-labeled groups very well. So let's break it down. Each customer is represented as a singular point in a multi-dimensional space where every feature, such as how often the customer visits or their spending habits, form one axis in that space. And our goal is to cluster all these individual points into a certain amount of groups. Before the algorithm even begins, you have to make one decision that the model cannot make for you, and that is choosing k, the number of clusters you will have. K-means will always force the data into k number of groups, even if the true structure is messier. It controls whether you end up with a few broad customer groups that are easy to act on, or many narrow subtypes that might be more precise but are harder to interpret and use. When people choose k in a careful way, they usually use methods that measure how much better the clustering becomes as k increases. Increasing the number of clusters almost always improves the accuracy in a mathematical sense, while also increasing the complexity in a practical sense. So the goal is to find the one value of k that gives you the most possible benefit without turning your results into an overcomplicated mess. One common method for choosing k is the elbow method. Essentially, you run k-means for several values of k, and for each one compute how far away the points are from their respective centers. This is measured with a number called the within cluster sum of squares, also often called inertia. Then on a graph, you compare how quickly the inertia drops as the value of k grows. At first, you often get big improvements because the algorithm is allowed to separate obviously different crowds. Then you reach a point where adding another cluster only gives you a very tiny improvement because you're most likely splitting a group that was already fairly coherent. The bend in the graph is the difference between the big improvements and the small improvements, and it's what most people consider a reasonable compromise. That is their value of k. Another method that gives slightly more insight is the silhouette score. In essence, it asks for every individual point whether it's closer to its currently assigned cluster or to its nearest neighboring cluster. It measures this by comparing the average distance from the point to other points in its currently assigned cluster against the average distance to points in the other nearest cluster. When the silhouette score is high, the clusters are separated and meaningful. And when the silhouette score is low, that means you're basically forcing boundaries through a messy cloud of points. In practice, you try different k values and look for the k value that gives you the strongest average silhouette score. Once you have chosen how many clusters you want, k-means begins by setting k initial centroids. Although the simplest approach is to pick these starting points randomly, modern implementations use smarter methods like k-means++. Essentially, it just chooses the initial centroids more strategically and spreads them out so you don't end up with the same two clusters sitting in a dense neighborhood while the rest of the data is ignored. That reduces the chance that the algorithm settles into a poor solution, and it usually makes convergence faster and more reliable. After initialization, the algorithm performs an assignment step. It's simple. Every data point is assigned to its closest centroid. Then the algorithm moves into its update phase. First, it moves each cluster centroid to the middle of the new points now representing it. That means each centroid becomes kind of a typical customer profile that summarizes the group. The algorithm then repeats the assignment and update steps over and over and over again. The algorithm is set up so that each step either improves the quality of the grouping or leaves it the same. Each reassignment moves the points towards the cluster center that represents them best under that current model. And each update moves the cluster center so it can better represent the group it describes. As a result, the process steadily moves towards a stable configuration rather than oscillating or getting worse over time. And that's why k-means is so great. But it's important to also understand where k-means might potentially mislead you. Essentially, it assumes that all groups can be sensibly represented by a tight, compact cluster. If your data contains clusters that are very different shapes and stretched, then k-means might not work very well here just because of the way the algorithm is set up. So instead, you might want to try out models like dbScan and the Gaussian mixture models. Nonetheless, once your k-means model is trained, you can use it to predict on new real-world data points. When the new data point arrives, you transform it in the exact same way as the training data and place that point onto the same coordinate grid you already drew. And you simply see which centroid it lands closest to and assign it to that cluster. And that is a full k-means clustering machine learning method breakdown for you. So if you'd like to see this coded out in Python, then don't forget to follow so you don't miss part 2. See you then.